One of the things we should learn to do in mathematics is, more than solving the problems, I would say even appreciate the problems. Even if you can't solve a problem, that's okay. So appreciating the problem is also just as important. Okay. So let me start discussing. I guess you're a little inhibited, at the moment to ask anything from the tutorial sheet. But yeah, if we were live and face to face, it would have been different. But particularly over long distances, it's very difficult for me if you do not give me your feedback. So it'd be very nice if some of you can ask questions, and doesn't matter if they are simple, doesn't matter if they are if you are unable to do the problem, that's fine. We can discuss some of the problems. So let me, since nobody seems to be forthcoming, let me set the ball rolling by asking you, describing the very first question on the very first tutorial sheet and asking your opinion of it. Okay, so here is the problem. So let A be an n by n matrix. What did you say? N by n matrix. So let me just see whether I used m by n or n by n. What did I do? What I did. N by n matrix. Okay, so let me, n by n matrix within real entries. Okay. Okay. Now, you can also consider this is also an n by n matrix with complex entries, right? Right? Is this clear? I mean, if a real number, I can also consider as a complex number. So the question here is: so what did we define? What did we define the minimal polynomial as? Of course, maybe we defined it for a linear operator rather than for a matrix, but the same definition works. So what is minimal polynomial? So the minimal polynomial, let's denote with PT of A, is the unique monic polynomial of least degree that A satisfies. Okay. Now, the other property is that it divides every polynomial that A satisfies. Right. So this is the definition of the minimum. So this exists over a this exists. So the idea is that I look at RT. I mean, I look at KT. Okay, let me use K, where K is a field over which these entries are. Everything is happening over K, right? I look at that polynomial ring and look at the ideal I, which is all those, let's say, FT in KT, such that when I put A into it, it becomes zero. I get the zero matrix. This is the matrix equation. Okay, this is I. Then this is an ideal. This is a non-zero ideal in A. Can somebody in KT, sorry. Can somebody tell me why this is non-zero?
At least characteristic polynomial will be there.
Very good, very good. Exactly. So non-zero because the characteristic polynomial Qt belongs to I. Very good. Excellent. Okay. So this is a monic polynomial of degree equal to n, degree n, that is there in the ideal. Okay. So there is at least one monic polynomial. There might be some monic polynomial of even lesser degree. If n is the least degree, then we take this characteristic polynomial. That itself will do it. If not, then we look for something lesser degree, and in fact something of least degree that satisfies, and we take that, and the claim is that it's unique, right? Let's not repeat those arguments. We understand that it is unique. So it is the generator of this idea. So I is generated by a unique polynomial. The generator is unique monic polynomial. And so if I can put the condition that the generator be generated by a monic polynomial, then the generator becomes unique. And this is called and that is called PT. Sorry, I'm repeating myself a lot. Okay, very good. Okay. Now the question is, if I look at, so I'll take a real matrix, do this over RT. Right? Consider this ideal over RT, and we get consider, and we have a minimal polynomial. It has a generator, unique monic generator, and we have a minimal polynomial PT. Okay. Now I can consider CT. Okay. Now I can consider I in CT. So that's an ideal in CT now. This K has, instead of R, it has become C, right? And we have, and again, it applies, the theorem applies. There's a unique monic generator, and we have a minimal polynomial. This time it is P prime T, let me call it. The question is, what? So this is the question. Let me put it in a different color. So this is finally we are asking the following question. What, if any, is the relationship between PT and P prime T? Okay, this I'll change. Let me write this. Okay. That's the question. Now, first, before we try to even bother answering the question, do we understand the question? I think it's a beautiful question. The first thing is to start appreciating the question. See, it's a rather fundamental one. I look at it over R, I get a polynomial. I look at it over C, and I get a polynomial over C. Right? What if, I can actually look at any field even bigger than C and look at it there. Any field containing R, and I'll get a polynomial over that field. What is the relationship between all these polynomials? That's the question.
So they will be equal?
They will be equal. Very good. And why so? Why is that?
Sir, because if we take minimal polynomial in over R, so we can take it in over C also, because C is extension of we can take. And because this P prime is a minimal polynomial in C already, then every minimal polynomial divides some other polynomial which kills.
So what you're saying is, let me
P prime T divides PT.
Very good. Very good. That is obvious from the P prime T divides PT from the definition. Because after all, this is a polynomial, this is a real polynomial which is satisfied, right? And this is a complex polynomial of least degree. This is true. This is from the definition. Indeed, that's very good. Yeah. But you are claiming they are equal.
Yes, sir. Because when we write it, this P prime T in complex complex numbers, then this is a polynomial. Maybe it can be of degree m. So we can take it as some T raised to power m plus complex coefficients into something T.
Yeah.
And when we equate imaginary part, real and imaginary part after putting A, substituting A, then both will be equal to 0, real and imaginary part. So
Okay.
then imaginary part, its degree will be less than m, and that's possible because we are already taking minimal polynomial of degree m. So
that's a very good idea. I was not thinking along those lines, but what you're saying is a very good idea. Very good idea. Very good idea. Go on, please. That's a very good idea.
So we will left with only real coefficients, because all imaginary coefficient will be 0, because that isn't possible with degree less than m, because already minimal polynomial of degree less m, that is of least degree. So when we are left with just real coefficients, then we have a polynomial that is killing A in reals, and PT already in reals, that is minimal polynomial, and therefore by definition PT will divide P prime. So both are dividing each other, therefore both are equal.
Because they are monic, both of them are monic. Yeah, very good. Excellent. Very good. Okay, let me, I'm so happy. That's a beautiful solution. Thank you, ma'am. May I know your name, please?
Sir, Anita.
Anita, which college are you from?
Sir, I am from Ludhiana, Punjab.
Very good, very good, very good, ma'am. Very nice. But I'll ask you, don't go away. I'll ask you a further question. Okay, but let me, for the benefit of everybody, let me repeat what I've understood of your solution, and you can correct me if I'm wrong. Okay?
Okay, sir.
Okay. So what she is saying, Anita from Ludhiana, is saying the following. So look, write P prime. So P prime T is a complex polynomial, right? So let me write it as or P1 prime T, right, which is the real part, plus I times P 2 prime T. Is this okay to write it like this? So yes, P1 prime T is a real part of, I'm just choosing the notation. You can write your, choose some different notation, doesn't matter. The real part of P prime T, and then P2 prime T is the complex part of, imaginary part of. Okay, very good. So then P prime T is, so now look at, so both these are real polynomials now, right? Now I put A into this. So P prime A is 0 because that is satisfied by A, right? And if you do that, you will get P1 prime A plus P2 prime. Okay, now what?
So now if we equate real imaginary, both P1 prime A and P2 prime A both will be equal to 0.
Right. So because A has only real part in it, right? A has only real numbers in it. When I compute this, this will be the so this will be 0 and this will be 0. Okay, so imagine this, that so this is a real polynomial. So this gives me something real and times I, right? So this whole thing is 0, means the real part is separately 0, the imaginary part is separately 0. And so this part is a real polynomial now, right? Which is of monic. So this, note that this is monic of the same degree as p prime. Okay, very good. Therefore, now this is so therefore this implies, or rather, sorry, it doesn't. It's a real polynomial which is satisfied. So p t divides p1 prime t by definition of pt. Because this is a real polynomial that is satisfied by a, pt must divide it. But it is monic of the same degree as p prime. So, but this is monic of the same degree as p prime. Okay, so the degree, I mean, you can argue this whichever way you want. So, so it turns out that pt or you can even say p2 prime. You can argue this in many ways. You can argue, for example, that p2 prime a has degree less than p prime t, right? Strictly less than p prime t, and it is satisfied by a, and therefore it it must be 0 polynomial, because it's of least degree non-zero polynomial. So this cannot be non-zero. So this is 0. You can say it like that. Okay, so p prime is indeed a real polynomial. Okay, that you can say it like that. But this shows that pt has a degree of pt. Another way to argue this with degree is degree of p prime t. So they are of the same degree, and one divides the other, and therefore they must be equal. Okay, thus pt equals p prime t. Very good. Thank you. Thank you, Anita ma'am. But let me ask you a question now. Right?
Yes, sir.
Okay, suppose we have, instead of real numbers, so I take a matrix, right, with just integer entries or something, right? So instead of RT, I can consider Q of T. How would you argue in that case?
I think if we take any field extension, their minimal polynomial will be equal.
Yes, that's correct. That's correct. The guess is correct. But how do you prove that? The reason why I'm asking this is that this kind of proof may be difficult to do there, right? So once again, this is a beautiful proof. It's correct proof, nice proof. And your answer also is correct. For any field extension, it doesn't matter, right? That's pt equals p prime t. No problem. That's correct. The guess of it's the correct answer. But why is it that? How do you prove that? Okay, so Anita ma'am, do you have you want to say something?
No, sir, maybe I think I'm a little confused.
No. What you say is absolutely, meaning your proof is absolutely correct in this case, and you're thinking from what I can infer from what you're saying, is that you're thinking along the right lines. Your answer is correct. Doesn't matter if I take K and any field extension K prime and look at the minimal polynomial here Pt and look at the minimal polynomial P prime T, they will be the same. That's correct. The only thing I'm sort of prodding you to think further is that you cannot do a proof like this, or at least we don't know how to do a proof like this, right? Or can you do a proof like this? Maybe that's another question. Okay, let's do the following. I'll give you 2 hints, okay? And maybe we can discuss it tomorrow.
Okay.
Right? Okay. But by the way, Anita ma'am, thank you so much. I really appreciate your response. And such responses are actually are quite reassuring for somebody like me, because by giving this response, you've given me assurance that, okay, what I'm saying is making sense and people are listening and it's making a difference. Okay. Without this assurance, I'm talking to I'm a blank screen, right? You understand what I'm saying? So,
Yes,
this is very reassuring for me. Thank you so much.
appreciating.
Hello, say that I didn't quite hear you, ma'am.
Thank you, sir, for appreciating.
Yeah, thank you. I mean, thanks are due to you. I mean, thank you so much. Thank you so much. Okay, and I hope you keep doing it. So here are the hints for thinking about this.
Okay, sir.
One is you can do a proof similar to this, except it becomes a little more complicated. So what you can do is you can think of, see, what is the point about real and imaginary parts? The thing is that you can think of C as a vector space over R. It's a field extension, but it's in particular, it's a vector space. Basis with 1, I being a basis. Right? So any matrix with complex coefficients can be written as a real matrix of the same size plus, the matrix can be divided into what we call real and imaginary parts. Those are precisely the coefficients of 1 and the coefficients of I. You see what I'm saying? So similarly, what you can do is, in more generally, you can think of K prime as a vector space over K. It's a field extension, right? So this is a field extension. And choose a basis. So let's call it some B alpha, something like that. And then you can repeat this thing by taking, you writing this P prime T as sigma over alpha B alpha into P alpha T, or P alpha prime T. And maybe you can make this with B alpha equal to 1 being the first element. So you can choose 1 itself as a basis, just like you choose here 1, right, as part of the basis. And so that will give you, so that becomes, so B alpha not equal to 1. Let me alpha not being the first element. I mean, this is an arbitrary basis, but one of them identified as alpha naught is 1, the identity of K. So then this becomes P alpha naught, sorry. It becomes monic of the same degree as P prime. And you can argue similarly. Okay, that's one way. That's one way of thinking about it. Second is actually even a little more abstract, but it's actually helps us revise a very important fact from linear algebra. Right? This follows from the procedure that we have for solving linear equations. Right? Given a set of linear equations, you, in this case, homogeneous linear equations, then you have a procedure for doing it, right? You reduce it, row reduce it, and then, I mean, this, as we all know, these are up to some changes in notation. It's the same procedure that is described in all the books, linear algebra books. From that procedure, what is clear is the following. So if you have a solution, so if a linear system of equations over K has no solution. So you can take a linear system of equations over some field, okay? And then solve it over this field, right? Then I can take the same linear system and think of it as a linear system over a larger field. No problem at all. We can do that, given any larger field. Then I can try to solve it over the larger field, right? The point is, if a linear system of equations over K has no solution, then, okay, I think I made a small mistake. No, it's okay. If a linear system of equations has no solution, then it does not admit a solution over any extension field K. This is a very important fact. Okay, if you use that, this, I mean, as somebody was pointing out last time, linear algebra is about solving equations, and indeed that comes up here. So this structure of this solution, I mean, the way you solve it comes up here, and from that you deduce this fact, right? This is something that we usually do not emphasize at that point. We just say, okay, this is how you solve a system, and then go on. But this is implied by that procedure. And if you apply that here, you will get it. Okay. So Anita ma'am, let me ask you, is this making sense, what I'm saying? The hint? Hello, am I audible?
Yes, sir.
Okay. Is this, am I making sense? If there is something you want me to explain, I can.
Sir, firstly, I will try.
Okay, good. Thank you. That's the spirit. Very good. Yeah. So this may look a little strange at the moment, what I'm saying, but if you think about it, see, when you write out these matrix equation, when you say something minimal polynomial equal to 0, what you're trying to solve for is the coefficients of the minimal polynomial, right? So you're trying to solve for the coefficients, and so, for example, there is no polynomial of degree less than p. So let's say the degree of p is d, right? And then there is no polynomial of lesser degree that is satisfied by these by a, which means 0. I mean, so not 0, which means a square, a cube, and so on up to a to the d minus 1. You know, these are linearly independent vectors in over the reals, right? Now you can think of that in terms of a solution of a linear equation and say that this system does not have a solution over the real numbers. It's a homogeneous system that does not have a so what am I saying? It's not quite a homogeneous. So they are linearly independent vectors over just give me a minute. Yeah. So there is the yeah. Just give me 1 minute, please. I'm just getting confused for a minute. Yeah. Okay. So what it means is it does not have a non-trivial solution. That's the thing. Okay. So okay. It does. So what it means, of course, it has. It's a. I got confused because it looks like a homogeneous system and it always has a solution. The thing is, this the way I've written it is maybe not the correct thing to say, because it's a homogeneous system and has a solution. So if a linear system of equations has no non-trivial solution, then it does not admit a non-trivial solution over any extension field. So this is the way to interpret it. What I've written is literally correct, but you have to correctly interpret it. I got confused because I was saying, I was thinking it's a homogeneous system, so it always has a solution, namely the zero solution. But the point is, the minimal, we are not interested in the zero solution. I mean, of course, the zero polynomial is always satisfied by a. What we are the existence of a minimal polynomial means, of a certain degree, means that an existence of a non-trivial solution to a system of linear equations. Okay. Yeah. So what I said is all right. Okay. Now let's go to another. Maybe I'll discuss another question. Okay. How about question number 3? Right. These are questions that perhaps you've seen and you understand. Maybe you know the answers, but they are worth going deeper into. Okay. So here is the other question. So prove or disprove every irreducible factor of the characteristic polynomial is also a factor of the minimal polynomial. Okay, this is the question. Okay. Anybody tried this, or anybody wants to guess the answer? Would you try to prove it, or would you try to disprove it? Anybody wants to try this? So maybe you can think of complex numbers to begin with. Over C, suppose our base field is C. Then I'm sure this is something you know and something maybe you all teach your students. Okay, before, let me ask you a more stupid question. Okay, and that is the following. So let me even write it as a stupid question. Suppose, okay, PQR, let's see. Suppose RT is a polynomial that is satisfied by A, the matrix A. Okay, is every irreducible factor of, so let me just, is every factor or at least every irreducible factor. So let me write it. There are two questions. Every factor, that's even more stupid, but irreducible factor of RT, also a factor of PT. So why is this question stupid? So by the Cayley-Hamilton theorem, you know that QT is a polynomial that is satisfied by A. Now I'm taking a general polynomial that is satisfied by A.
So maybe it is a fact that every polynomial which is satisfied by A will have same roots. Maybe roots will be different in algebraic multiplicity, but they will have same roots.
Okay.
Minimal polynomial, and they
no, but okay. So let's see. Could you repeat what you said?
It means I was saying that every polynomial.
Yeah, I heard what you said. But I am a little hesitant. So I ask you to repeat. I'm putting it in red, right? Every polynomial. So RT is any polynomial that is satisfied by A. You're saying that, let's just think over C. Every linear factor of RT is also a factor of PT. Is this what you're saying?
Yes, sir.
Are you sure?
So yes, because minimal polynomial.
So for example, if PT, let's say, is t minus 1 into t minus 2. Okay, just for example. Okay.
Yes, sir.
Now, if I take anything that is divisible by P also satisfies A, right? So RT could well be t minus 1 into t minus 2 into t minus 3. So t minus 3 need not be in PT.
So no, means t minus 3 will be also present in PT.
No, in this case, how about this? Suppose I take the matrix A. This is my matrix 1, 2, 0, 0. What is its minimal polynomial? T minus 1 into T minus 2.
T minus 2.
Suppose, does it satisfy this polynomial, RT?
Yes, sir.
Yeah, we can actually work it out. So what you get, T minus, if I put A minus 1, I get 0, 0, 0, minus 1. T minus 2 will give me minus 1, 0, 0, 0. T minus 3 will give me minus 2, 0, 0, minus 1. And multiply these matrices, I get 0, 0, 0. Okay, so it does satisfy. So any polynomial that PT divides satisfies it, but you can just add some factor, right? Is this clear?
Yes, sir.
So that's why this is a rather stupid question. That's why this is a stupid question, because this is of course not. No. If I take some, so here is an example. You can take RT to be, I can put a T minus 4. I know, as long as T minus 1 and T minus 2 are there, you can multiply by something that only makes it worse, right? I mean, it is satisfied even more. A will satisfy it even more. So you cannot expect that just because this polynomial is satisfied by A, every factor or every irreducible factor of RT need not be a factor of PT. Okay, so but here we are asking about the characteristic polynomial. So this is R of A. Was it Anita ma'am again who responded?
Yes, sir.
Okay. So is this clear? I can explain again. But is this have I?
Yes, sir.
Okay. Now let's come back to this. For the characteristic polynomial, this is being asked. Is this true or false? That's the question. Here, of course, the characteristic polynomial is just T minus 1 into T minus 2. This T minus 2 or T minus 4 or some other factor will not appear as the characteristic polynomial, will not appear as a factor in the characteristic polynomial. So in this case, it's definitely true because they're equal. The characteristic polynomial and minimal polynomial are equal in this case.
So that means in practice, if we take characteristic polynomial, then this result will be true?
This will be true. Indeed, it is. Indeed, it is true. Right? But how do you prove this? So the answer is yes. Right? The statement is correct. Okay, let me ask. Every factor of the characteristic polynomial is also a factor without the irreducible. How about that? That's again a stupid question. So what is a counter example to that? I'm giving you a hint. I'm saying it's a stupid question. So if I don't put this irreducible, every factor of the characteristic polynomial is also a factor of the minimal polynomial. What is wrong with that statement? You understand the question, right? So suppose I'm removing this irreducible. So suppose, so this is, I'm circling this, maybe in a different color, and highlight it. Suppose I remove that. How about that statement? Will it still be yes or no?
So it maybe not every factor means every factor algebraic multiplicity maybe can be changed. Power maybe can change. Maybe,
so yeah, correct. But how do you answer that question? Meaning, smart answers to stupid questions. It's, I don't know if you have heard that phrase. So what is the smart answer to this? You're right. You're right. It's not true. And it's important that it be the irreducible factor. And what you said is also correct. The power could be higher, right? But okay, here is what, take qt itself. That's a factor that need not divide the minimal polynomial. So an example would be, take the identity matrix. So for example, so this is, so once again, let me write it in this color. Okay. So here, so this is false if we remove the irreducible. Okay, and here is an example. Just take A to be the identity matrix. Not 1 cross 1. In that case, it will be true. So what is the, so here, what is qt?
So x minus 1 whole square.
Yeah, t, so, right, x minus 1. Since the variable is t, I'm going to write t minus 1 square. And what's the minimal polynomial?
So that will be t minus 1.
T minus 1. So indeed, so this factor, qt itself is a factor of qt. And that does not divide pt. Right? So qt itself is a factor of qt. And in general, qt not equal to pt. So this is not possible. Right? pt always divides qt, no problem. But there is no reason for qt to divide pt in general. Okay. So, however, the characteristic polynomial has a special property that every irreducible factor of the characteristic polynomial is also a factor of the minimal polynomial. The question is, how do you prove this? So now the burden now is, so we have answered yes, and now we are asking for a proof of it. How do you prove that? Okay, so let me just mention that one, okay, you may come up with some nice proof. In fact, I must say that I was not thinking of this proof of real and imaginary parts. I was more thinking in these abstract terms, this item 2, the hint 2 that I have given, right? I was thinking in those terms, but Anita ma'am's proof of breaking it into real and imaginary parts is a much more simple and straightforward proof, okay? Except that there is this problem. This proof works for any field extension. This proof seems to work only, the way it's phrased at least, only for R and C. But actually, you can do this proof also in more general, in greater generality. So what I was going to say is that in my mind, at least, the proof that I have in mind for 3 uses this statement about 1, that the minimal polynomial is the same when I do a field extension. But maybe you can maybe you have another idea, some other idea, and you will come up with some different proof. It's quite possible. So how about we discuss more about this tomorrow? Okay, if you have, we'll have a lot of things to discuss tomorrow. Meaning there's a lot, there'll be there is this tutorial sheet. There was another tutorial sheet that I distributed this morning. Maybe I'll distribute one more tutorial sheet later this evening. So there will be a lot to discuss. Depends on what you want to discuss. Okay. So with that, let me move on to, let's move on to another question. How about number 4, right? On the tutorial sheet. Did anyone try, or should we discuss it tomorrow if nobody tried? So let me remind you. So if AT and BT are polynomials, right, and CT is given to be the GCD of these two, of AT and BT. DT is given to be the LCM of these two. The question is to show kernel of CA is equal to kernel of AA intersect kernel of BA, and kernel of DA equal to kernel of AA plus kernel of B. So A is again a sum n cross n matrix. A is any square matrix. So in a sense, there is just this to the primary as indicated in the exercise. The primary decomposition theorem will follow from this if we can show this. And this itself is a very, these are fairly simple things to prove once you get the idea. Okay. Any comments on this? Somebody tried it. You want to try it now? You have an idea? We can discuss. Or should we do it tomorrow? If anybody tried it and didn't get it, if you tried it and didn't get it, you should ask, or if you tried it and got it, describe the solution, please. See, the one thing that bears repetition is we cannot learn mathematics by just, I would say just attending lectures is just not done. I mean, you have to pose questions and try to answer them. Right? That's the whole point of the process of learning mathematics. And that's why we are having this, all these workshops, etc., where we are trying to emphasize the need to solve questions, think about things. I mean, just there are many textbooks. Just looking at those textbooks and sort of parrot-wise, just repeating what is there, or just reading what is there, or listening to lectures is not really so effective. Finally, one has to get one's hands dirty, and one has to start thinking. One has to make mistakes, realize the mistakes, go back. It's an active process where your mind is you're asking questions and you're being alert all the time. Okay. Once again, may I request you for some response? I'm lost. without any response. I'm not even sure I'm being audible.
You're audible only, sir.
Okay. Okay, I'm lost as to what to do. Okay, maybe let me take it that nobody tried this question, right? And so I repeat, the proof of primary decomposition, which we discussed last time, is just based on this, right? And these don't look so unfamiliar. If you have looked at ideals in Z, they sort of look like this, right? The ideal generated by A and intersect the ideal generated by B is the ideal generated by the LCM. The ideal generated by A plus the ideal generated by B is the ideal generated by the GCD. So this looks slightly different. We are taking kernels. I mean, there's some difference, but so in terms of ideals, it goes the smaller the polynomial, the bigger the ideal. Here it's the reverse. The smaller the polynomial, the smaller the kernel. The smaller the kernel. So there is a slight, there is some inversion of inclusions, but for that it's the same idea. Okay, so let me go on. Since there is no response, I assume that you will try this by tomorrow, and I assume that maybe nobody has tried it. And so let me go on to asking you another question. So from the next tutorial sheet, which was distributed earlier today, so tutorial sheet on so let's look at the tutorial sheet. What it does is actually it gives you the proof of JCF. So what I wanted to do in today's lecture is actually outlined in the tutorial sheet. Okay, so I feel relieved of the burden of having to prove it, because the proof is a bit complicated, not in its ideas, but the idea is very simple. And the best way to understand the idea is through problems. Okay, so here is a problem. Okay, suppose I have, so here is a question in its simplest form. So V is a finite dimensional vector space, and T is a linear transformation. Okay, suppose T square is 0. Okay, let's say dimension of V is T. Okay, question is, let me see the way it is phrased. So it says, what values can dime TV have or take in terms of D? That's the question. So let's look at that. Well, maybe you can think about this. This is a simple question. Let's think about it now, whether or not you've thought about it before. Once again, I want to emphasize the point about appreciating the question. See, each questions these are like puzzles, right? These are like brain teasers or riddles that you see in newspapers, that maybe you're used to working some out. Right? Now, for a puzzle to be to really be interesting, it must intrigue you, right? There must be there is some hurdle there that you are supposed to cross, right? If you cannot see the hurdle, then you have no appreciation for the puzzle. Right? I mean, whether or not you can solve the puzzle, you should first appreciate the puzzle. That's the first step. So solving mathematics problems comes later than appreciating them. Many times, maybe we can solve them because we just remember something that our teacher told and we just do it, right? But we perhaps do not appreciate what's going on. So that's true, but what I suggest is we sort of start appreciating questions, right? So, for example, I've called this a stupid question. I mean, I don't take the word stupid as some, I've called it a stupid question because it's really, there is no puzzle in this, right? It's rather stupid. Here, there is a puzzle in here. Every irreducible factor of the characteristic polynomial. If I leave out the irreducible, then again it becomes stupid. But if every irreducible factor of the characteristic polynomial is also a factor of the minimal polynomial, that is what gives the tightness to the question. And that makes it interesting. The answer is yes, it's true, right? So unlike the answers to the stupid questions, the stupid versions of the question, the answer there is clearly no. Here the answer is yes, but it's not clear at all. You have to use some property of Qt, right? Okay. Similarly, so what is the point here in this question? So we are asking for the dimension of TV. So what can it be so if I take a linear operator on V, what can the dimension of TV be? It's the range, right? What can it be? In terms of D, what can the dimension of this TV be? Anybody wants to respond, please? I'm lost as to. Maybe I'm asking too stupid a question. But this question is not stupid. Meaning, with the t square equal to 0, it's not stupid. But without that, just take I'm asking, suppose I don't put this condition. Remove this. Without this. Then the question is really stupid. And what is the answer? What values can this TV have? The dimension of TV have?
Is it d squared, sir?
No, this is dimension of TV, the range of T, right?
So maybe we can use a rank nullity theorem.
Yeah.
Maybe.
Yeah, no, but you can use the rank nullity theorem, correct? But just the image, without this, first let's ask the stupid question. So I don't put this condition t square equal to 0. I just ask, you understand what this means, right? TV is the range of T. What can the range of TV is a subspace of V, right?
D or less than D.
D or less than D. Correct. So the answer to the stupid question is, dimension of TV in general is less than or equal to D. That's all you can say. And all values 0, 1, 2, up to D are possible, correct? You can construct linear transformations that take on any of these values. Right? You can construct matrices, linear transformations are the same as square matrices, right? Which have ranks 0, 1, 2, d. For example, take the matrix 1 and rest of them, everything else 0. Now this has rank 1, which means the dimension of TV is 1. If I take this matrix, for example, I mean, this is not the only matrix, but there are lots of matrices. These are some simple examples. All the rest are 0, right? So this has dimension 2 and so on, right? This has the range of this has dimension 2 and so on. Okay. Okay. Now I put the condition that t square is 0. Now what is the answer? That now there is I've introduced something into the puzzle. Now it's a puzzle, not a very difficult puzzle, but still, what is
D plus 1?
It can't be d plus. What do you mean? The total number you mean? Sorry, when you say d plus 1, what do you mean? So the general linear transformation itself can have values 0, 1, 2 up to d. What we are asking is, suppose t square is 0, right? So I take a square matrix. Say let's say 10 by 10 matrix. If d is 10, so you take a d by d matrix, T, or A if you call it, right? Some d by d matrix. And A square is 0. And then the question is, what is the rank of it? What values can the rank of A take?
The t square equal to 0, then kernel of t contain an image of t.
So kernel of t is contained in
The image of
no, not the other way. No, say that correct. Your idea is correct, ma'am. Kernel of t. It's not contained in the image of t, but
Kernel of t square.
Kernel of t, yes, and the image of t. What's the relation between them? Which is contained in which? T square is 0 means which is contained in which? Your idea is correct. I didn't mean to stop you. I only heard it maybe incorrectly. That's why I asked you. So which is the larger thing, given that t square is 0? So if I take something in TV, so it's something in TV. So this is any general image element of the image is of the form TV, right? If I apply t once more, that's going to become 0, right? So this image is contained in the kernel of t. I heard it as you said, kernel of t is contained in the image of t.
Yes, yes, image of t contained in kernel.
Okay, is that okay?
Yes,
do you agree with
okay,
that?
yes, sir.
Okay, now answer this
Thank
question. Yeah, now answer the question, please. Yes, this is in fact, you have hit the nail on the head. This is what is relevant. But using this, and somebody said rank nullity theorem. I think it was Anita ma'am who said rank nullity theorem. So yeah, use this now and the rank nullity theorem, and then you have the answer. So what does the rank nullity theorem say?
Dimension of V equal to rank of T plus nullity of T.
Dimension of V, which is D, what we have taken, right?
Yes,
is equal to dimension
of range plus dimension of kernel.
Dimension of kernel of T, sorry, not T,
yes,
kernel of T plus this dimension of T.
Range. Yeah.
Which is T. So I'm asking you about this. So now what is the answer? Can it take all these values or are some of them excluded? That's the question. You see this and see this. For example, if this were D minus 1, what would be what would happen to dimension of kernel of T?
1.
It would be
1, sir.
1, sir.
It would be 1, but look at this. If this is D is 10, say, so then D minus 1 is 9. Here it is 1. A 9-dimensional space will be contained in a 1-dimensional space. Is that possible?
No, sir. No, sir.
So together, these two together imply some constraint on these numbers. What is that constraint? These two numbers add up to D, and this number is bigger than this number. This number is bigger than this number, and these two numbers add up to D. So what can this number be? So for example, if D is 10, right? Can this be 9? Can this dimension be 9? If this were 9, then this would be bigger than 9 or bigger. So this would be minimum 18. There is no way it can add up. So if this is 9, this is 1, but that cannot be because this is 9. This number has to be bigger than this number.
0. Yes.
0 is okay. Yeah. Anything else? If this is 0, this is D. That's okay. If this is 1, then this is
D minus 1.
Oh, would that be all right? Will 1 be less than D minus 1? Depends on D, of course. Let's say D to be 10. Let's fix D to be 10. Right. And in that case, what is D minus 1? If this is 1, this is 9. Is that possible? At least this says that it's possible. Of course, we have to construct, but that's a different matter. But for the moment, let us just work out the constraint that is imposed by these two conditions. So what it says is, since we are running out of time, I'm telling you the answer, is that it says that dimension of TV must be less than or equal to D by 2. So for example, if D is 10, then dimension of TV can only be, the values can be 0, 1, 2, 3, 4, 5. It can't be larger than that. If it was bigger than 5, say 6, then this would have to be bigger than 6. Right? But because of this. But then the total has to add up to 10. That's not possible. So this puts a constraint on the dimension of T, the dimension of the range. Okay. Okay, this is a very simple thing. I mean, this uses nothing more than rank nullity and this, but this is the basic idea. That is, I mean, I wouldn't say more ideas are involved, but this is sort of one of the basic ideas that underlies the JCF. Okay. Anyway, we are out of time, so let us stop for today. And like I said, I'll try to distribute one more tutorial sheet for what it's worth. So the point again is we may not be able to discuss all the problems that I'm going to, that are on this sheet or on the previous sheets fully in tomorrow. But that doesn't matter. You can always try them later. I'm happy to, if you have any questions later on, to be contacted by email to answer those questions if you have. Yeah. And anyway, it is good for us to try these questions even beyond the lecture. So I want to emphasize again, without thinking about questions, without engaging with questions, without actually you coming, I even tell my son who's studying now 11th and 12th, it's not enough that you solve the questions I give you, right? You should be able to pose interesting questions to me, right? Questions that interest me, meaning that the